Good morning. In this video, we're going to talk to you about rational and irrational numbers. This is something we covered right before Christmas break, and it's something that's going to show up on Illuminate next Friday. So again, this video lesson, the goal of it is for us to reteach some ideas about what a rational and irrational number is. By the time you're watching this video, you already should have done part 1 for the guided practice, that is to read and analyze today's objectives. Since some of you didn't, we're going to go ahead and take a quick look at the objectives and the key terms, but you need to start reading this on your own. The big thing to understand today for rational numbers is that a rational number is a number that can be written as the ratio of two integers. That's a really fancy way to say any number that we can write as a fraction in the form a over b, where a and b are whole numbers, is going to be rational. So to simplify that even more, if we can write a number as a fraction, it's going to be rational. And that tells us that an irrational number, the opposite of a rational number, are all the numbers that cannot be written as a ratio between two integers. What's an integer? Integers are whole numbers, but they include the negatives, so -4 is an integer, just like +4 is an integer. One thing that we're going to be realizing by the end of today is that the irrational numbers, the only type of numbers that cannot be written as the ratio of two integers, are non-terminating. That means the decimal never stops. And they're non-repeating. If they have a pattern, or if they're terminating decimal, we can always write them as a fraction. So let's take a look at the guided problems for today. We're also going to start using the whiteboard right now, which I'm going to flip to. And the whiteboard is going to kind of help us make sense of which numbers in the world are rational and which numbers in the world are irrational. First part of guided problems today asks you what makes a number rational. The whole key at the end of the day is our first objective. Can we write it as a fraction, as a ratio of two integers? So for part 1, you should be writing about the idea that rational numbers are something we can write as the ratio of two integers, or something we can put as a fraction. So we're going to start to discuss now which categories of numbers can be classified as rational, or in other words, which kinds of numbers can be written as fractions. We're going to look at a cheat sheet real quick, or a note sheet that I put together for you all that can help us categorize which numbers are the rational numbers and which numbers are the irrational numbers at the end of the day. So if you take a look here at this cheat sheet, we're going to start looking down. We're going to take the whiteboard a lot bigger and look at different types of numbers that could be called rational based on what we see here. So go ahead and pause this video right now. Take a look at this cheat sheet, or this note sheet, and start saying to yourself, which categories of numbers could we call as rational? Welcome back. The first type of number that we should be realizing is rational are all of the integers. I'm going to use integers, and that covers whole numbers, natural numbers. It gives us all the positives and negatives. So let's talk about that for a second. Every single integer, for example, if I have the integer -8, can easily be written as a ratio -8/1. We could do that for every single whole number. All we do is take the whole number, the integer, and put it over 1, and now it's as a ratio or a rational number. Let's take a look at the cheat sheet again for another type of number. We see here as we get outside of the bubble of integers, there's still a whole big set of numbers, different numbers that qualify as rational. Fractions, no matter how complicated or ugly, even if you don't like fractions, every single fraction, by definition, has to be rational. Every single fraction, even something ugly like -17/3, still has to be rational at the end of the day because it's already a fraction. It's already a ratio. Next up, any decimal that terminates. So right here we see 0.75. We'll use that as an example. We're going to say any terminating decimal has to be rational. 0.75, if you remember in 5th grade, the correct way to say this number is 75 hundredths. If you think back to scientific notation in base 10, every decimal number, no matter how tiny, no matter how complicated, could be written as a negative power of 10. And negative powers of 10 really just mean whatever the coefficient is divided by a bunch of powers of 10, 100, 1,000, whatever it might be. Terminating decimals, and you can talk to us more if you have questions. No matter how complicated, if the decimal comes to a stop, we could always make it a fraction, so it always has to be rational. As we're running out of room on the whiteboard here, I'm going to erase those three. Keep looking. What other types of numbers could be considered rational? I'm going to point two more out for you. The fourth one I would put on my list is going to be repeating decimals, and I'm going to show you what we mean by that. Take a look. The one repeating decimal they show us on the cheat sheet is 0.33, and this tells us the 3 keeps repeating if we see a line over it. So for repeating decimals, go ahead and full screen that again. A repeating decimal like 0.3 really came from the fraction 1/3. And as we talked about a couple weeks ago, right before Christmas break, I guess that's a month ago, every single repeating decimal, no matter how complicated it is, came from a fraction. And if you want to get a little bit deeper and figure out how do I always convert repeating decimals to fractions, I'm happy to talk more about that. The last one we should pick up and realize, square roots, not all of them. So you'll see the square root of 8 is an irrational number, which we'll show in a second. But some square roots, like the square root of 16, let's take a look at that. The square root of 16 is just going to give us 4. So the opposite of the square root of 16 would just give us -4. But you're going to notice it's only some square roots that are rational. Other square roots, when we took a look at our list, they showed us the square root of 8. The square root of 8 has to be irrational. We'll take a look here. Square root of 8. You should be familiar now that all of the square roots that were not perfect squares gave us these messy irrational decimals. So we'll go ahead and take a look at square root of 8 one more time. 2.8284. So if we put 2.8284, there's no pattern, would put a ... And what we're going to recognize, importantly, all of the irrational numbers, pi, 3.1415, and it keeps going with a crazy pattern. Every single irrational number is really, at the end of the day, just one of these ... numbers. Pi, we know, is 3.14.15, keeps going, and we know a lot of the square roots are these ... numbers. Any of the square roots that don't make integers or perfect squares end up being irrational. So going back to the guided problems, taking a look, there are 2 more problems you should be able to do on your own now. Could you classify this number, an ugly decimal 2.16, and then the 6 keeps repeating, as rational? If we paid attention to our list, take a look here, you should know the answer to part 3 now. Same thing for part 4. Are square roots rational or irrational? Well, at the end of the day, we know some of the square roots will be rational, but other square roots will not be rational. Let us know if you have any questions. The rest of the guided practice is going to be having you work through lists and say which numbers are rational or irrational, and then explain why some numbers are rational or irrational.